All right, so my name's Jacob Davis. I'm a graduate student at the University of Washington, the Applied Physics Lab, and I work with Jim Thompson over there. So I'm going to talk today on some measurements we've been taking in hurricanes using wave buoys. And in particular, I'm going to talk about the spatial distribution of wave slopes in hurricanes. So this is just a satellite image of Hurricane Idalia, which is the hurricane I'm going to talk about, which made landfall. It's from the past summer, this hurricane season. It made landfall in the Big Bend region of Florida. So we've been doing these targeted deployments of these small drifting wave buoys into storms. You might be familiar with some of these buoys. But so first in the center of the screen, this is a map of the Big Bend region of Florida right there. For some context, this is Florida. That's the track of the hurricane. It was a Category 3 at landfall. And we went ahead a couple of days ahead of the storm with the help of the NRL Scientific Development Squadron and deployed this array of buoys right here. So we deployed 3 different types. In the top left, that's the MicroSwift, which we developed at UW APL. It's about 1.5 feet tall and 4 inches diameter. And then you might be familiar with the SOFAR Spotter, which is a slightly larger beach ball-sized buoy that we put out through the door of the airplane. And we also work with a team from Scripps in the Lagrangian Drifter Laboratory using the directional wave spectra drifters, and they have different types. But this is one that is so-called A-sized, so like the MicroSwift, it's small and cylindrical, and it actually fits through a chute in the airplane. Okay, so I'm going to talk about, we've been focusing on observing the mean square slope. This is the mean square slope measured by the buoys, but just in general, right, the mean square slope is related to the gradient of the surface, right? So the gradient of the surface squared, take the average. And the reason we are interested in it is because it's a proxy for surface roughness, right? So for example, if you were able to resolve enough of eta, right, all the wavelengths, then for example, this is 2 different surfaces that have the same average roughness, but they have different mean square slopes. The one on the top, oops, those are backwards. The one on the top has a high mean square slope, ignore that. And then one on the bottom has a low mean square slope, right? So they look very different in terms of roughness. There's also been some work showing that mean square slope is related to form drag, some parameterizations, and this is a result, a snapshot, or a clip I took from the Sullivan 2018 paper, of flow at the onset of braking. In that paper, they then kind of describe mean square slope as one of the primary variables that correlates with their measurements of form drag. And so we've been measuring this through 2 different means. First, just using the buoy, it comes from the spectrum. It's the 4th moment of the spectrum. And we've been finding that when we go and do these measurements in hurricanes, the mean square slope is having a tendency to saturate with wind speed, whereas in lower wind speeds, a lot of work, right, Cox and Monk, right, show that resolving even out to these really small wavelengths, it has a linear dependence. We are, with the buoy, only able to resolve waves greater than 6 meters or half a hertz, which are pretty large waves compared to Cox and Monk. But still, we find they're linear at these lower wind speeds and then saturate around 20-25 meters per second. We've also been using some measurements from the Wide Swath Radar Altimeter, the WSRA, which is a radar that flies on board the Hurricane Hunter P3s, and using this geometric optics model right here, by looking at the backscatter from 0 to 14 degrees off nadir, you can determine the mean square slope using this model. And we are finding that we also see saturation, or a similar behavior with wind speed in the WSRA mean square slopes. So we're seeing this trend in 2 different instruments and are trying to understand it better. And so, right, we know that mean square slope has this primary dependence on wind speed, especially at low wind speeds, where it tends to be linear. But what we're wondering is with this data set we've collected in Hurricane Idalia, which is much more spatially dense, if we can find and uncover any secondary dependencies on the hurricane itself and how it varies within the storm. So this is a little movie showing, again, the Big Bend region of Florida and the hurricane passing by. These are wind speeds from the COAMS-TC model, which is a model operated by the Naval Research Lab and some of our co-authors. And it's just showing how the hurricane passes through the array of buoys, and the colors are just showing the different types. And so first things first, taking this data from Idalia and plotting it on top of our Fiona and Ian data from the plot I just showed you, we find that it has a similar tendency, or has a similar behavior. But now what we can do is with this data set, we can start to look at things in a storm following reference frame. So on the right-hand side here, what I have done is I put all the measurements, the drift tracks, in the frame as if you were, sort of sitting on the hurricane and always aligned in the direction of its heading. And so I have at 0, 0 the center of the storm, and then we have the x and y distance as you get further away. Here I've normalized it by the radius of maximum winds, which is mostly constant over this 15-hour period. And then what I've done here is I've taken those buoy observations in time, and I've colored their mean square slope on this color scale right here, so as it gets redder, the mean square slope is higher. But really, we don't glean a whole lot from this plot, right? Because the mean square slope is generally higher closer to the center of the storm where the wind speeds are higher. And so to indicate the wind speed and also the structure of the storm, I have these radii plotted right here, which show the 34 knot winds, the extent of the 50 knot winds, and the extent of the 64 knot winds. So we can see there's kind of some asymmetry right here, where we have this larger region right here. We see this sort of darker clusters kind of closer to the center of the storm. So instead, what we've started to do is we take a very simple fit, a TNH fit to the data, in this case to the orange dots only in Hurricane Idalia, and then we start to look at the residuals. And so here I'm plotting the residuals to our, using our fit, right? So the observed mean square slope minus the fit, and I'm plotting this in the same reference frame. And now I'm coloring the residuals that are positive in red and the negative residuals in blue, so higher than the fit, less than the fit. And we were finding this very distinct spatial pattern, particularly that the the mean square slope residuals are actually higher in the rear right quadrant. So having removed this dependence on wind speed, there's this spatial pattern emerging. And so what I want to do for this talk, we kind of want to go through and kind of give this laundry list of possible causes and kind of walk through each of them and see if we can find one that makes the most sense, at least in this very empirical approach. So let's go from top to bottom. Wave development, right? For example, we're looking at things in the storm reference frame, but the waves that we're looking at down here were once ahead of the storm, right? So you could think that, well, these waves have been experiencing hurricane winds for longer. Might that be the cause of this effect? But if you look at this, we are in these different sections of the storm. Each of these dots are going to be spaced an hour because these are how often the buoys report the measurements. And we're in these different parts of the storm for multiple hours, right? 6 hours, for example, in this region right here. And we think the response time at the mean square slope is based on some previous work, probably in the order of an hour, or in these wind speeds, probably even faster. So that might not really be what we're seeing here. Currents could definitely play a big role, right? Wave current interactions. We'll learn about that a lot. Hear a lot more about that later this week. And also potentially, right, a Doppler shift due to the currents. But what we keep coming back to is that we're making these observations with drifting buoys, and so we think we're making them in the intrinsic reference frame. So we're not necessarily having like a very explicit Doppler shift due to the fact that we're in a moving platform like an airplane. And also, as far as Doppler shift due to the fact that the traveling, propagating through a gradient in currents, we're kind of more focused on the local wind wave generation. We're not necessarily following these waves along a ray path where that that energy conservation principle would be important. So we're still wrestling with this one, but we're going to keep moving on. And I'm happy to talk more about it later. And then moving on, depth dependence. Of course, we're taking these measurements pretty close to the coast. Right, this was just before landfall. So here I'm showing the bathymetry in the Big Bend region, and we can see most of the buoy data points are between about 20 and 40 or 50 meters. And so what I can do is we can also look at, in this reference frame, we can look at the depth measured from each buoy. And so here is that. And just sort of looking between the two, looking for kind of similar spatial patterns. There might be a little bit, right? I'm coloring the depth, so deeper waters are in dark blue, less deep waters are in this sort of lighter yellow-green color. And of course, we do see, some of the observations over here tend to be in shallower depths where we are seeing the higher mean square slope residuals. But when we go and look at the actual, versus wind speed, mean square slope versus wind speed with our fit, we're really finding kind of just scatter around that fit. We're not sort of seeing separation above and below like we're looking for. So we don't really think depth is totally answering this question, especially because we're looking at the waves in the tail, at least closer to tens of meters, right, where the depth effects are relatively kind of still deep, or at least intermediate. Next, the wave age, or in this case, the inverse wave age. Here I'm taking U10 from the model, and I'm comparing it to an energy-weighted phase speed, or sorry, group speed, and or phase speed. And what I'm doing is I'm plotting the inverse wave age in this storm following reference frame, same as our residuals. And what we find is that, obviously most of these waves are young, and especially the closer you get to the center of the storm. And we're finding it doesn't really separate our data relative to this fit, right? It's definitely separating it sort of in wind speed, right? It's almost more of a predictor of wind speed, especially because it's in the metric itself, right? So that's not really explaining our residuals again. But finally, if we turn to this another metric, the wind wave misalignment, right, where I'm just taking the wind direction from the model, and I'm comparing that to, again, in this case, the energy-weighted wave direction as measured by the buoys. I'm looking at the difference and the absolute difference. And I'm actually, in this case, I'm sort of categorizing it in this bulk, in the sort of bulk sense, where I'm saying everything between, wind wave misalignment plus or minus 45 degrees on either end, I'm going to call aligned waves. Crossing is going to be where you're perpendicular plus or minus 45 degrees from 90 degrees relative to the wind. And then we don't have any cases in this case, in this particular storm, but we also have opposing waves where we are, plus or minus 45 degrees from 180 from the wind. So I'm coloring aligned in blue, and in this case, crossing in gray, just to sort of get some bigger picture patterns. And we find that this actually seems to, just kind of qualitatively by eye, right? It seems like it's having, it looks the most similar spatially to our residuals. And if we then turn to our plot of mean square slope versus wind speed, we find that this metric seems to really, waves that are following that are better aligned tend to really lie above our fit, and waves that are crossing tend to lie below it, at least in this region, less than probably 30 meters per second. So we're seeing this connection between our residuals of mean square slope and this wind wave misalignment. And this is encouraging because there's been recent work showing connection between the air-sea drag coefficient and wind wave alignment, which follows a very, has a similar spatial pattern. And their argument is that, the air-sea drag coefficient, or their observations rather, are that the air-sea drag coefficient is higher when the wind and waves are aligned, just like the mean square slope observations we're seeing. And so to summarize that a little better, this is one of the plots I took from their paper, and this is Zhao et al. 2022. What they say is they find the drag coefficient is lower in the far front and the left front quadrant of the storm, where you tend to see more misaligned swell, as opposed to us, where we're seeing more aligned wind waves in the sort of rear right quadrant of the storm. And what they've done is here they're showing their observations of drag coefficient as a function of wind wave misalignment, and they find that it might peak maybe around like 30 degrees, but it's generally higher when you have wind and waves more aligned, and decreases as the wind and waves become increasingly misaligned. And we again see a similar effect both spatially and in this sort of sense with our residuals. They tend to be higher where the wind and waves are aligned, and decrease as we become increasingly misaligned. And the same is true of also just the mean square slope observations themselves. And so in conclusion, we've been deploying these drifting wave buoys as part of our Napa hurricane coastal impacts to measure waves in storms with high spatial density. And this high density is starting to enable us to explore the wave spatial patterns, having simultaneous measurements in all quadrants of the storm at one snapshot in time. We're finding that the mean square slope as measured by the buoys has this dependence on wind wave alignment. It correlates with it at least. And this is also true of the drag coefficient, right? And so it's suggesting that these two are related, maybe causal, but definitely at least related. And we have one more season of data collection, so we're really excited about that. And this one is actually, the upcoming season is forecast to be a pretty active one. So this is just a forecast from Colorado State University, where they're finding that there's going to be, the average for the past 30 years has been, about 14 named storms. They're projecting to, 23 named storms, and so on. So it's forecast to be an active season, and we have we're hoping to get some more dense data sets like this so we can start to look at, how this might depend more broadly on information about the storm itself, the size, the strength, the speed. So with that, I welcome any questions, and thank you.